So my name is just Tallan. I work primarily on the processing side of the Cert 3D project. I work with Dr. John McCloy. So we've been primarily focused on the production of ceramic windows or optical ceramics. So here's just a brief overview of our process flow. So depending on what we decide to do, we either start out with commercialized powders that we buy from different manufacturers, or at certain times we've also tried the co-precipitation method to produce our own powders in-house. And then after we've produced our powders, there's a lot of pre-treatments that we have to do to make them suitable for producing high-density ceramics. So in this case, mostly we've done calcination and other drying processes to dry them out, but in the future, we're probably going to look into some more advanced techniques to increase our powder flowability and things like that. And then once we have our powders ready to work with, we then pack them into a die of some sort. We have both the die in our hot uniaxial press, which is a carbon die, and we also use a stainless steel die at times that we just use in a normal pellet press to produce what you call our green body pellets. And then after we produced our somewhat densified green body, we then use hot uniaxial pressing or just vacuum sintering to try and densify the product further. And then once we've completed that, we do some post-sintering processing, primarily annealing, and then we also do polishing and grinding to try and move surface defects and things away from that. And then after that, we can finally do our analysis to see what we've actually produced. So just to give you a little bit of a viewpoint of what we have, that image on, I believe would be your left, is the hot uniaxial press. You can kind of see it's a pretty small chamber, and these rams right here, these are carbon rams, and this is a carbon reducer that we use because our actual die press that we use is slightly smaller than the outside diameter of these rams. And then on the other side, we have our Archimedes style density tester that we use to test the density of our ceramics. So density is very, very important in producing high quality optical ceramics. So having that information is very, very important. So the way that we've been analyzing the results of our processing are primarily by FTIR analysis and seeing how close we can get to the maximum theoretical transmittance for our given systems. So if you're not familiar with transmittance calculations or optic calculations, I won't go into it too much, but basically you have this transmittance value, which is largely affected by, in a perfect world, only the refractive index of your material, which is your N value right here. And depending on your N value, you can calculate your reflectance, and from your reflectance, you can transmit or calculate your transmittance T. And you also have some amount of absorbance, which in a perfect material and a perfect bulk material is hopefully very, very low. And that information can kind of be used to calculate our refractive index and thus our maximum transmittance, which is what in a perfect world with no defects, with no inclusions or anything, would be the highest transmittance that we could achieve. And we see for a pure yttrium system in the wavelengths that we're interested in, we can achieve between about 85 and slightly over 90% transmittance. So that's kind of what we were shooting for going into our experimentation. So for our density calculations or measurements that we'll show later on, there are a couple of important considerations that you need to be aware of. So what we found a lot of the time was that during the sintering process, because we were sintering in a high carbon environment in a carbon die, there was actually diffusion of carbon into our final sintered product, which then would later come out during the annealing process and leave vacancies and decrease the density of our product. And the important thing to remember is that we basically produced one large chunk for each of our compositions and sintering conditions, and then broken into smaller chunks that were then annealed and had post-treatments done on them. But depending on where that final chunk that was heat treated and things like that came from, it'll be differently affected by the amount of carbon that diffused into the actual pellet. So if the chunk that we chose to do annealing on happened to come from the outside edge that had more carbon diffusion, that has an artificially lower density than a chunk that would come from the center of the pellet that would have less carbon diffused into it.
What's your pellet diameter?
So the pellet diameters that we did were 1 inch diameter, and they varied in thickness depending on what green body density we could get and how much sintering went on and how effective our densification processes were. So we also looked at our powders under SEM imaging. We found that we basically had two sets of powders. We had our commercially sourced powder, which I usually call the macro scale powder, which is this somewhat regularly shaped 3 to 5 micron diameter yttrium oxide powder, pure yttrium oxide powder. And then we had our second set of powders that were produced via the co-precipitation method, which you can see here, which are much smaller. They're usually in the order of 100 to 150 nanometers, but you can see that they have a completely different morphology. They almost have this weird platelet snowflake type geometry. And they also were very, very prone to forming these large agglomerates that you can see here, which initially we thought that these large agglomerates were a problem, but we've since discovered that perhaps some degree of agglomeration is actually ideal, and I'll get into that later when we discuss the outcomes of some of our experimentations. But it is important to notice that the two powders we used in our experiments were very different and had very different outcomes. So the first set of pellets that we produced were using this commercial powder that we have, this more macro scale powder. And we can see basically these are the conditions that we use to sinter our pellets. We would heat them linearly from about room temperature all the way up to our sintering condition, in this case 1600 degrees C. We'd then allow them to dwell for 15 minutes, and then we'd again pretty linearly ramp them down to lower temperature before releasing the force during this ramp down, and then we'd have our finished product. And after doing annealing at different conditions, we're able to see the different transmittance values and the different densities that we were able to achieve. We found that our as-sintered density was 97.1%, and then as we annealed, our density actually went down, which again is due to the presence of the carbon in the as-sintered pellet, and then as that carbon leaves, it then leaves basically empty spaces or air, which of course has a lower density than our solid product. And we found here that we were able to achieve right around 35 to 40% transmittance, varying a little bit depending on the annealing conditions, which corresponds to an approximately 50% loss from the ideal condition of transmittance. We also did XRD analysis on our pellets to determine basically what phase was present in our Y2O samples. We were curious whether we'd see any inclusions that were separate phases or things like that, but upon doing XRD analysis, we found that we were basically only seeing Bixbyite Y2O3, which is exactly what we expected, and we weren't able to see any impurities or other phases. But the caveat on that is that I believe our XRD is only able to detect about 0.5% impurities. So if the impurities are a smaller fraction than that, we can't see them with the XRD, and we have to use a different technique such as Raman to look for them. So here we can kind of go through just several other samples we found. We saw here these pellets were sintered at a same temperature, 1600 degrees C, but for a longer time of 30 minutes. And we can actually see that we're starting to get some light through the pellets. It's a little bit hard to see on this top left as sintered image, but in the image I can see, and in the real pellet, you're actually able to see some transmittance through the pellet, and then we get slightly more transmittance as we increase our annealing temperature before seeing a decrease in transmittance once we reach even higher annealing temperatures. And then as we go on, we see again 1650 degrees C, 15 minutes of annealing time, and we see again some transmittance, but not quite as much. So these samples were not quite as well sintered and not quite as well densified. And you can see that corresponds in the transmittance data. And then finally, we go to our most productive sample that we have right here, which was our sample that was sintered at 1700 degrees C for 15 minutes. We can see that at least up until 1250 degrees of annealing temperature, we were able to get some optical transparency. And we were able to see relatively good transmittance up to about 40% again on these samples. And the interesting thing that we noticed is that the density on this highly transparent sample is not markedly different than the density on our less transparent samples. So that tells us that I believe there's an issue with
A little bit lower, right?
the transmittance is interesting. So when you're using the FTIR sample holder, you have to mask parts of it off. And because our samples are irregularly shaped, it's not always possible to perfectly cut off the edges. So sometimes, even though what you have is more optically transparent than you'd expect, when you're going to measure it, because it's an irregular shape, and you might be cutting off one of the highly transparent areas, which in the future, when we rerun more experiments, we won't be subdividing our pellets to the same degree and things like that. So we'll be able to look through only the center of the pellet, which has the lowest carbon content of the high edge transmittance. So it'll give us a better idea of what we're looking at. We also did EBSD mapping to look at our pellets. We only really looked at the most successful EBSD pellet, or mapped the the highest quality pellet that we had, because a lot of the other pellets were broken down to do XRD analysis and other things on that, and we wanted to optimize our time. We can see fairly regular grain structure, which is what we're looking for in our pellets. There's not as huge of a grain size distribution as you saw in some of the other pellets that we made that I'm not going to talk about, that are made from like cerium oxide and things that had very irregular grain structure. And this grain structure is similar to what we'd expect to see from literature and highly transparent yttrium oxide samples, which tells us that as far as our grain sizing and things like that, we're on the right track. We just need to twiddle more with the density of our samples and mostly with the impurities of our samples to get high optical transparency. And are there any questions?